Hey everyone, how's everyone doing? I hope you're all doing well. Welcome. This will be part of a mini-series where I'll be covering maths, chemistry, and physics topics and condensing them to short summary videos for your leisure. In this video, we'll be going through differentiation and we'll be covering the topics of differentiation, the product rule, the quotient rule, and also the chain rule. Before getting started, I highly recommend downloading the notes in the bio below so you can annotate and follow through the video. Alrighty, differentiation. So this is probably the first time that you probably come across this topic or this word even, but differentiation is basically a form of calculus. And what it is when you differentiate a function, it'll give you the gradient function, which allows us to find the gradient at a specific point on the graph. So in layman's terms, whenever you get given a function, if you apply the method of differentiation to it, you basically get what is called a gradient function. And that basically allows you to find any gradient along that function at any given point. So let's get into it. A differentiated function can be denoted by either y dash or dy dx. So basically, to show your gradient function, when you apply differentiation, you can show that gradient function, that differentiated function or gradient function as y dash or dy dx. So throughout this whole topic, you either see y dash or dy dx. So, and your teacher might use one or the other, and they might be a bit more partial to one than the other. So the general rule for differentiation is that if y is equal to ax to the power of n, that being just an ordinary function with a power, then the differentiated function dy dx is equal to anx to the power of n minus 1, right? So that's just the general rule for differentiation. But if that means nothing to you at all, that's all good. We'll go through an example below. So for example, let's look at example 1. So you've got y is equal to 3x squared plus 2x minus 5, which is just your normal quadratic function, right? That function can also be written as 3x squared plus 2x to the power of 1, but we never show to the power of 1 because we just assume it's to the power of 1, minus 5x to the power of 0. Anything to the power of 0 is 1, hence it's just 5, right? But if you wanted to write it out with all its powers, it would look like that, right? So if you wanted to find the gradient function or the differentiated function, all you have to do is go y dash or dy dx and is equal to. So what this rule basically means is that you're bringing down the power to the front and you're minusing it by 1. So for example, if you look at 3x squared here, what you're doing is you're bringing that 2 to the bottom. So it's going to be 3 times 2, which gives you 6. And then that power of 2, you're going to subtract 1. So instead of power of 2, it'll be power of 1. That's why you're left with 6x, right? So for example, and then you do the same thing for the next one. So now you're looking at 2x to the power of 1. So once again, bringing the power down to the front. So it becomes 1 times 2, which is just 2. And then now your power sign, subtract 1. So it's just 0. So then you're left with x to the power of 0, which is just 1. So you're left with just 2, right? And then you do it on to the next one. So technically speaking, whenever it's a constant, so if it's just a number by itself with no x, no variable next to it, whenever you differentiate that, it just becomes 0, because what ultimately happens is that you're bringing down a 0 to the front. Anything multiplied by 0 gets eliminated and becomes 0. Cool. So that's how differentiation works. So let's have a look at something that's a bit more complex. So looking at the function y is equal to 5 multiplied by square root x. You can also write this in the power form. I always recommend my students putting their functions into a power form before differentiating because it actually makes your life a lot easier. So hot tip. So once again, if you wanted to differentiate this, so you got y dash dy dx is equal to, right, so looking at this guy here, once again, following the differentiation rule above, you're pulling down the power to the front. So then it's 5 multiplied by half, and then obviously subtracting 1 to the power. So half minus 1 will give you negative half, right? So 5 times half, x to the power of negative half, which is equal to 5 over 2 root x. Cool. If you're wondering why that root x is at the bottom, it's because anything to the power of half just means it's a square root, right? As you can see, square root x is equal to x to the power of half. Same thing with this. However, whenever you've got a negative power, you're basically putting it at the denominator. Cool. Having a look at moving on, having a look at example 3. So now you've got some brackets. So when you get given a function like this, it's easiest just to expand it out first. So if you expand this guy, you get 2s to the power of 3 minus 3x squared plus 2s minus 3. Once again, if you differentiate it, you do the exact same thing as we did in question 1. So I'll just go through it real quick. Bring the power of 3 to the bottom. bring the power 3 to the front, so it's 3 times 2 gives you 6, and then obviously subtract 1 from the power again, so you get s to the power of 2. Same thing with this guy, bring the 2 to the front, 3 times 2 is 6, and then subtract 1 for the 2, so you got just to the power of 1, so it's just s, and then 2s, technically there's a power of 1 there, bring the power of 1 to the front, and it becomes 2 times 1, and then obviously subtract 1, take 1 is 0. So anything to the power of 0 is just 1, so you're left with 2. So a quick tip as well is whenever you're differentiating a term that only has a variable to the power of 1, it will just end up being the constant, the number that's in front of it. And then if you have a constant, once again, that just disappears to 0. That's just a quick method. Instead of actually doing this in your head, you can, if you remember that, it's a lot quicker to do. And eventually over time, as you do more and more differentiation questions, you'll get used to it. One thing I also wanted to just call out, in this case, the function is in terms of t and s, right? That's why for the differentiated function or the gradient function, we denote, instead of using y dash, we use t dash because that's what the function starts with, right? And then instead of dy dx, we use dt ds because it's t in terms of s. That's why we write it as dt ds. And I don't know if you guys have noticed, same thing, this is y in terms of x, that's why we write dy dx, right? That's just the convention that we use. Just follow that. Cool. So moving on. So sometimes you get functions that are a bit more complex and you actually, it's not as easy to use the general differentiation formula. That's why we'll learn a couple of other sort of rules and formulas to help us sort of navigate and differentiate more complicated looking functions, right? So the next rule that we come across is called the product rule, right? Which is another form of differentiation, which is also differentiation for more complex functions. So consider the function y is equal to x multiplied by x plus 3. When you have a product of two functions, use the product rule to differentiate. Product of two functions, you got x multiplied by x plus 3, so 2. Product of two functions. So if y is equal to fx, fx representing the first function x, and gx multiplied by gx representing the second function, then dy dx, the differentiated function or the gradient function, is equal to gx multiplied by f dash x. F dash x just basically means the differentiated function of f of x plus f of x multiplied by g dash x. Or in layman's terms, you can write it as if y is equal to u times v, where u is the first function and v is the second function, then y dash to get the differentiated function or the gradient function, it's equal to u, so the first function multiplied by the differentiated function of v, the second function, plus v multiplied by u dash, which is the differentiated function of the first function. All right. Once again, if that means nothing to you, that's why we've got some examples down here so we can understand it a bit better. Cool. So looking at example 1, you've got the function y is equal to bracket 3x minus 5, bracket x squared plus 5x minus 7, right? It's a product of two functions. Using the more simplified product rule, you can basically let u equal to 3x minus 5, which represents the first function, and we can let v equal to x squared plus 5x minus 7, which is the second function. So using the product rule, so y dash, we're going to basically implement this guy, right? Cool. So this is just v, which is this guy here. Then u dash, which is basically u, but differentiated. So if you differentiate that, you only get 3. That's why it's 3. And then plus u v dash. So that guy there is just u by itself. And that guy there is v dash, which is that differentiated, right? And then obviously just open the brackets, right? And you get that. And then just collect like terms, right? So the differentiated function or the gradient function of this guy using the product rule is this guy over there, right? So very similarly, if you get something a bit more funky like this guy, once again, whenever you get square roots, I highly recommend you writing it out in its power form. So obviously x square root of x3 is just x to the power of 3 over 2, right? So we can rewrite this function into this function here. So very similarly, just like the question before, let u equal x to the power of 3 over 2. Let that be our first function, and let v equals 2x plus 1, which is our second function. So using the product rule, once again, you grab u by itself, right, multiplied by v dash, which is just that differentiated, plus u dash, which is this guy differentiated, multiplied by v, which is just that guy again. Cool. And then if you expand brackets, you get this, and this is basically your gradient function or differentiated function. Cool. All right, moving on. So another rule that we come across is called the quotient rule, right? So once again, we're learning this rule because we might get given a function that is a bit more complex looking, and it's harder to just basically use the general formula that we learned there. Right? So for the quotient rule, consider the function y is equal to 3x minus 5 over 5x minus 7, right? When you have the quotient of two functions, use the quotient rule, right? So if you have a look at that function there, it's actually two functions, one at the top over one at the bottom. Cool. So once again, using the same nomenclature, y is equal if y is equal to u over v, then y dash is equal to uv dash take vu dash over v squared, right? So going through the examples, if you look at example 1, you've got y is equal to 3x minus 5 over 5x minus 7. So let u equal 3x minus 5 and v equal 5x minus 7. Using the quotient rule, so using this guy above, dy dx is equal to, once again, so v is just that guy over there, multiplied by the differentiated version of that, multiplied by u dash, which is just the differentiated version of that, which is 3. Take away u, 3x minus 5, multiplied by v dash, which is just basically the differentiated version of that, and you get 5, over v squared. Cool. That is equal to 4 over 5x minus 7 squared. Cool. So similarly, example 2 is exactly the same. You do the exact same thing. Let u be the top function and let v be the bottom function, right? Using the quotient rule, you're doing the exact same thing. Cool. Okay, so last but not least, you've got the chain rule, right? So this is probably the most complex one to get your head around, but it's actually the most common one that we'll be using in terms of questions when you're being assessed. So let's say we are not directly given y in terms of x, but instead given y in terms of some other variable u, and given this other variable u in terms of x, right? So slightly confusing, but we'll kind of go through it, yeah? So we can still get dy dx. That's what we're originally chasing after, right? Using the chain rule. So for example, if y is equal to f of u, so if y is equal to a function in terms of u, and u is equal to g of x, which is u is in terms of x. So to find dy dx, what you'd have to do is you'd have to differentiate this function, in which you'll get dy over du, and you'll differentiate this function, in which you'll get du over dx, right? And if you multiply the two differentiated functions, dy du multiplied by du dx, what happens is, what you can basically do is cancel out the du's, right? And what you're left with is dy dx, and that's what you're actually trying to find. Cool. So that's the process of the chain rule on a basic level, right? But it gets more fun. So let's go through an example real quick. Find dy dx in terms of x, given that y is equal to u squared minus 5u, and u is equal to 7x minus 3. Right? Once again, two functions. So one is y in terms of u, one is u in terms of x. Right? So first, let's find dy du. Right? So differentiate this guy, you get tu, you get 2u minus 5. And differentiate this guy, so you get du dx is equal to 7. So using the chain rule, we want to multiply these two guys together because the du's will cancel out and you're left with dy dx. So what you do is just multiply the two functions together, multiply the two different, so what you do is you multiply the two differentiated functions together, right? And you get this guy. But then what you want to do is you want to substitute the u with what you want to substitute the u back in terms of x, which is this guy here. So u is equal to 7x minus 3. So substitute this guy into u, and you get this guy, right? So now you've got your dy over dx, your differentiated function, in terms of y and x. Cool. So that's sort of like a long process of using the chain rule. There's actually a shortcut method in which, as you do more questions, you pick this up and you actually become really quick and efficient with it, right? So the shortcut method of the chain rule goes, if y is equal to the function of x to the power of n, then dy dx, or the differentiated function or the gradient function, is equal to n. So where you've brought the power to the front, very similar to the general equation that we learned at the very beginning. F of x to the power of n minus 1 multiplied by the differentiated function, right, of f of x. F multiplied by f dash x, so the differentiated function of fx. Right, so let's go through an example to see what that actually looks like. Right, so for example, you get a function like this: y is equal to x squared plus 3x plus 1 bracket to the power of 6. Right, so using this guy, what you want to do is you want to pull that power to the front. Right, remember to always minus your power, so now it's to the power of 5. And also you're going to differentiate your original function, and that's going to be multiplied to the end result. Right, so if you differentiate the original function, you'll get 2x plus 3. So you tack on 2x plus 3 at the end, right? And that will be your differentiator function. And that's how you use the shortcut method of the chain rule. All right, so very similar. If you look at example 2, you've got y is equal to bracket x to the power of 3 plus 1 bracket to the power of negative 1. Once again, bring that power down to the front, so you get negative 1 minus 1, we get negative 2, and then you want to differentiate your function, which is just going to be 3x squared, and you just tack on 3x squared at the end. Right. Once again, whenever you've got a negative power, it means that you're just putting it down to the denominator. That's why it looks like that. Cool. Cool. So one thing that I should also add before we wrap up this video is that you can also use the main function on the classmate using dy dx to differentiate function. So if the question allows you to use your classmate, use those capabilities, 100% implore that. But if not, what we went through today are the ways in how you basically differentiate by hand. Cool. Well, that sums up this video. Hope you guys found it interesting, took something out of it. Once again, if you guys are chasing these notes, they're just in the link in the bio below. I'll catch you guys in the next one. See ya.